Oh, yes. Oh, hi. My name is Xin Theta and Perimeter Institute. And today I'm going to talk about my work with Daniel Siegel about to include the neutrino fast flavor conversion in the neutron-star post-merger disk, accretion disk. Okay, so as we know from the GW17-OA17 that there will be a kilonova counterpart following the neutron-star merger events. And this kilonova is usually seen by two components. One of the blue kilonova comes from the neutron pool ejector, usually come from the dynamically ejector phase. And then there will be a red component with the neutron-rich ejector from the accretion disk. And this accretion disk is really a very hot and dense environment with a lot of neutrino produced, and with luminosity up to 10 to the 52 to 10 to the 53 ergs per second. And this neutrino can really change the nucleosynthesis through the weak interactions. And for the neutrino fast flavor conversion that comes from the self-interaction among the different neutrino species, which can lead to the nanosecond timescale for the exponential growth of these off-diagonal terms, which is essentially mixing the different flavors of the neutrino species. And here's some previous work done by other people for some post-processing to estimate whether the neutrino fast flavor conversion will take place in a collapsar simulation and the neutron-star merger remnants. So in this work, we perform a GRMHD simulation with the neutrino radiation transport. And this work is adapted following the M1 method given by Shibata and adapted from the Zellman code developed by Luke Roberts. We trace 4 species with 6 energy beings. And to include the fast flavor conversion into the simulation, we took this dispersion relation approach where we calculate the maximum growth rate for each grid and set the neutrino flavor to be equipartition among neutrinos and antineutrinos if the growth rate is fast enough. And we start with the simulation from equilibrium torus of 0.07 solar mass around the 3 solar mass black hole. And we evolve this simulation to 400 milliseconds compared with the 2 simulation with and without fast flavor conversion included. And we measure this accretion rate. Initially, it can be as high as 1 solar mass per second, which is really high and above the R process threshold. So R process will be activated. So here's are the 2 snapshots from the simulation with fast flavor conversion. And on the top layer shows the density, and the bottom half shows the growth rate for the fast flavor instability. And you can see initially, this fast flavor conversion is ignited everywhere outside the neutron sphere, and later it diffuses into almost everywhere inside the disk. And in our simulations, most of the ejector is along the polar region, with is along the equatorial plane, with very few come from this polar region. And so here are the 2 snapshots of the electron fraction comparison between the simulation with and without neutrino fast flavor conversion. And we see with fast flavor conversion turns on, the ejector becomes more neutron-rich, while the inner part keeps neutron electron YE quite low through such a self-regularization process. And the spatial gradient, there's also a spatial gradient of YE in both simulations. And this is consistent with the GW17-OA17 indicating initially blue supernova turning into a red supernova, kilonova turning into a red kilonova. Okay, and how does the YE get reduced in the fast flavor conversion? Because electron and anti-electron neutrinos are more copiously emitted in the post-merger disks. And once fast flavor conversion turns on, it essentially reduces both electron and anti-electron neutrinos into the other species. In other words, it reduces the electron and anti-electron neutrinos while increasing the other components. to test this results on, to see how this affect the R process nucleosynthesis, we run the simulation with Skynet for the R process calculations. And here are the two comparisons. So first, the green line shows the simulation without fast flavor conversion. And you can see here with the neutrino produced, it actually reduced the lanthanide production and also the third peak in this abundances plot. However, when the fast flavor conversion is turning on, it reduces the electron and anti-electron neutrinos and restore the lanthanide abundances back to the solar value shown by the red dots on the plot on the right. Okay. So in conclusion, we performed GRMHD simulations with the neutrino fast flavor conversion included dynamically. This post-merger disk has a very high initial accretion rate, about 1 solar mass per second, and showing a radial gradient of YE, indicating early bluer kilonova emissions turning into redder emissions, similar to this GW170817. And fast flavor conversion is found to boost the R process lanthanide abundances close to the solar values. And that's more or less I want to talk about. Thank you very much.